Hi friends, this is Sarvajan here. Welcome to my networking channel. Hope all are doing good. And today the topic I'm going to discuss about OSPF. OSPF is a open standard, so open shortest path first algorithm it uses. And let us now understand the OSPF process. So OSPF, the entire network is divided into area. So the main area we call it as a backbone area. So all other area will connect to this backbone area. So the main area we call it as a backbone area. On all other areas should connect to the backbone area. That is the OSPF architecture. And let us see the OSPF features. So it supports VLSM and classless protocol. So what is a VLSM? Is a variable length subnet mask. So in an internet network, I can have subnet mask of variable length, and also I can use different networks. So it support also the classless routing protocol. So what is a classless protocol? So while sending the routing updates, it will send the subnet mask information along with the routing updates. So that is the reason we call it as a classless. So it is a link state routing protocol, and it advertises its state of link, whether the link is up or down, and all the information. It will advertise to the neighboring routers in the form of link state advertisements, and it supports discontinuous networks. So in a single network, I can have multiple different networks, and also I can use subnet mask of varying length. So that's the reason we call it as a discontinuous networks, and it converges very quickly. Why? Instead of sending the entire routing table, only the updated changed information will update to the neighboring routers. So and it also reduces the routing overhead, and it has an administrative distance of 110. So OSPF uses the Dijkstra Shortest Path algorithm for finding the best path to the remote network. So what is a link state advertisement? So OSPF advertises its state of link, whether the link is up or down, to the neighboring routers in the form of LSA, what we call it as a link state advertisements. And LSAs are additionally refreshed every 30 minutes. So every 30 minutes, it will send the LSA to the neighboring routers. And also whenever there is a change to any of the link, it will update to the neighboring routers. So it always send the triggered updates. That's any change updates, it will update to the neighboring routers in the form of link state advertisements. So what is a OSPF router ID? So it is a 32-bit binary number elected by the router. So it is used to uniquely identify the each and every router. We call this a router ID. So how it is elected? It is elected by the router with the highest loopback address or the highest IP address. So if a router ID changes, you have to always do the clear IP OSPF process. So these are the key points of OSPF router ID. How OSPF calculates the metric, uses a cost as a metric for finding the best path. So how the cost is calculated is cost is equal to reference bandwidth divided by an interface bandwidth. So in this manner the cost is calculated. So OSPF uses cost as a metric for finding the best path. So now let us understand what is a OSPF designated router. So DR is selected by the router with the highest priority or with the highest router ID. So assume it is always selected the multi-access network where we have multiple different routers, right? R1, R2 and R3. So assume R1 is selected as a router ID. So always R1, R2 and R3 all are using the default priority. So in that case, it will go for the highest router ID. So router ID can be highest IP address or the highest loopback address. So assume R1 is having a highest IP address. So this will be elected as a DR, and R2 will be elected as a BDR. So the second highest IP address or the second highest router ID will be elected as a BDR, that is a backup designated router. And another one is R3. So the R3, if the priority is 0, if it is neither DR nor BDR, so this will be elected as a DR other. So that is the reason we call this as a DR other. So one will elect as a DR, BDR and DR other. So DR uses 224.0.0.5 to notify any changes. So if this DR router, if any link goes down, it will notify to other router with the multicast address 224.0.0.5. So once this router receives the change, it will update to the DR using the multicast address 224.0.0.6. So these are the key points you have to keep it in mind about the OSPF designated router. So what are the tables it builds? OSPF, like other routing protocol, OSPF build a topology database. So what is a topology database? So it contains the summary of all the link state advertisements, right? So this information we updated in the topology or a LSDB database. So the neighbor table or the adjacency database contain all the information about the neighboring routers. So once it find the best paths, always the best path information we find in the routing table. That is, it contains the best path to the remote network, right? So these are the OSPF tables. So what are the packet types? So hello packet, it is used for establishing the neighbor relationship, and DPD packet for exchanging the link state databases. So first is a hello packet. So always OSPF exchanges hello packet for establishing the neighbor relationship between the two different routers. and DBD packet for exchanging any link state database. So always you will exchange the information in the form of LSDB, that is a link state databases. What is the LSR packet? So LSR packet is a link state request packet. So assume that I am connected R1 and R2. So R1, if it requests any update, it will send a link state request to the neighboring router asking for an update. So that is a link state request. So when the adjacent router receives the update, you will send a link state update to this R1. So once R1 receives the update packet, you will send a LS acknowledgement packet for that update packet. So these are the OSPF packet types. So what is allow and the dead interval? OSPF allow and the dead interval. So allow interval is used for establishing the neighbor relationship, and dead interval is the amount of time it waits before declaring the neighbor dead. So the default allow interval is 10 and dead interval is 40 for broadcast and a point-to-point network, and the default allow interval is 30 and the dead interval is 120 for a non-broadcast and a point-to-multipoint network. So always keep it in mind, dead interval should be 4 times the allow interval, and both the routers allow and the dead interval should match on both the routers. So now let us see when the OSPF routers will not form adjacency. Under what situation the router will not form neighbor relationship or adjacency with each other. So the first scenario is both routers should be configured in the same area. If both are in the different area, then this will not form a adjacency with this neighboring router. And also the hello and the data interval should match on both the routers. If it does not match, this R1 will not form a neighbor relationship with this R2. And also both the routers should be in the same network type. So the default network is broadcast. Assume this router is configured in broadcast and this is configured in a non-broadcast. In that scenario also both the routers will not form a neighbor relationship. Let us understand the OSPF network types. One is a broadcast multi-access. An example is an Ethernet. So in case of broadcast multi-access, we should elect DR, BDR. And since it's a broadcast, the neighbors will be determined automatically. And the DR, BDR to other routers multicast address is 224.0.0.5. And traffic to DR is 224.0.0.6. And what about point to point? So example is T1 link where two routers are directly connected. So since only two routers are there, there is no need for DR-BDR election because DR-BDR election is always mandatory in a multi-access network. Since only we have two routers connected, so since it is treated as a broadcast network, I already told default behavior for point to point is broadcast. So in that scenario, neighbors are determined automatically. And the multicast address is 224.0.0.5 and point to multipoint. An example is point to multipoint frame relay network. So in this scenario, OSPF will not elect DR-BDR. So in this scenario also there are two things. One is a broadcast and a non-broadcast. So assume this is a broadcast. In this case, neighbors will be determined automatically and OSPF will not elect DR and the BDR. And what about non-broadcast multi-access? Example is a frame relay network. OSPF will elect DR and BDR and the neighbors should be manually specified. Since it is a non-broadcast, the neighbors are not determined automatically. We have to manually configure the neighbors. So now let us understand the OSPF stages. So first stage is down. So assume R1 and R2 are connected. So indicates that no hellos received from the neighboring router. So that means it is in a down stage. So init is, let us say R1, it is sending the hello packet to R2. So R2 will add the R1 router ID to its neighbor. So that is a init stage. So when R2 added the neighbor of R1, it will again send a reply back to R1. So that is a two-way stage. That means when R1 sees its own router ID in the neighbor hello packet received from R2, so that is a two-way. Bidirectional communication has been established between R1 and R2. So that is a two-way stage. So then it will be in a process of electing the master and the slave relationship. So then what happened? One will be elected as a master and the other one will be elected as a slave. So for exchanging the databases, that is a LSDB databases. So that stage is called as a extort stage. So that is the process of electing the master slave relationship. So once it is elected, then it will be synchronized with the database, exchanging the link state databases, what we call it as the exchange state. So it is always exchanging the DBD packet, that is a database descriptors. And load is a loading stage. Assume both the routers are not yet synchronized. It's a process of loading all the LSDB database. Assume R1 does not have any update. It will send a link state request to the neighboring router and R2 will send a link state update. So when it's a process of synchronization, what we call it as a loading stage. So when both R1 and R2 completely synchronize with the LSDB database, we call it as a full stage. So let us understand OSPF hierarchical design. So this I have connected three areas, area 2, area 0 and area 1. As per the OSPF rule, always all the areas should be connected to the main area, what we call it as a backbone area. It's labeled as area 0. So all should connect to the backbone area. So what is the purpose of area? To reduce the size of the routing table, right? So assume there is a single big area without any segmentation. What happen? The SPF algorithm will be more. So each and every time any changes happen, each and every time it will run a SPF algorithm, and the routing table will be large in case of a single area. So that is the reason we are segregating into a multiple area to reduce the size of the routing table and also to reduce the SPF algorithm. So what are the area types? Standard area which accepts all the link updates and the summary. Backbone area is the area 0. What we call it as a labeled as an area 0 is the backbone area. So to this backbone area, all other areas should connect, right? This is a centralized area to which all other areas connect. And what is the stub area? So assume area 2 I am configuring as a stub area is used to block the external routes. That's the routes from a non-OSPF domain. So what are the information it contains? It contains the intra-area route. That is within the same area, intra-area routes, and the routes from other areas. That's what we call it as an inter-area routes and a default route. So what about totally stub area? It not only blocks the external routes, it also blocks the routes from other areas. So that is the purpose of totally stub area. So what are the information it contains is intra-area routes. That's the routes within an area and a default route. And what about a not so stubby area? So it contains the type 1 and a type 2 LSA. And also in this case, ASBR generate a special kind of LSA, what we call it as a type 7 LSA. So what we call it as a not so stubby area. So now let us understand the type of LSA. Type 1, type 2, type 3 and type 4 LSA. So type 1 is a router LSA. So this LSA is generated within an area, what we call it as a type 1 or a router LSA. And network LSA is generated in a multi-access environment. In a case of DR election, so the LSA generated by a DR we call it as a network LSA. So what is a summary LSA? So this router assume generate a type 1 LSA. When it reaches ABR, ABR will generate a type 3 LSA and it pushes to the backbone area. So this is a type 3 LSA, what we call it as a summary LSA. And a type 4 LSA is generated by ABR. So it is generated by an ABR which contains a route to an ASBR. That is a type 4 LSA. So also called as an ASBR summary LSA. And type 5 LSA is generated by an ASBR which contains the route to an external autonomous system. So that is a type 5 LSA. And type 7 LSA is generated by an ASBR. So now let us understand the type of routers. One is an internal routers. Assume if all the routers that exist within a same autonomous system. So the routers that all the interfaces within a same area, what we call it as an internal routers. So these all the routers will be having the same LSDB link state databases. And what is a backbone router is nothing but which interconnect all the routers, or we can say the router that sit in the perimeter of the backbone area. So this is the backbone router, right? So this sit in the perimeter of the backbone area, what we call it as a backbone routers. So at least one area should connect to this backbone area. And what about area border router? This is an area border router which performs the inter-area route summarization. So it is used to summarize routes from other areas. So this we call it as the area border router which performs the inter-area route summarization. And ASBR performs the external route summarization. So this is an ABR is an area border router and ASBR performs the external route summarization. It is used to summarize routes from a non-OSPF domain. So that is the purpose of ASBR. So that is the difference between ABR and ASBR. ABR performs the inter-area route summarization and ASBR performs the external route summarization. And what about OSPF Virtual Link? So assume I already told all the areas should be connected to the backbone area. So in this area, there are two disconnected areas. Area 2 and Area 1 are not connected to this. Area 2 is not connected to Area 0. In this scenario, I can create a virtual link between Area 2 and Area 1. So that is the purpose of OSPF Virtual Link. So what is the OSPF summarization? I already told there are two types of summarization, inter-area route summarization and external route summarization. In this architecture I told, right? So ABR performs the summary routes from other areas, that is an ABR, and autonomous system router performs the external route summarization that is used to summarize the routes from an external area. So that is done by ASBR. So ABR performs the inter-area route summarization. So what are OSPF authentication? There are two types of authentication. One is the plain authentication. So where authentication is done using the plain text, and MD5 is authentication is done using a MD5 digest. So I hope you enjoy all these videos. So I'm going to explain each and every scenario in a lab. So I'm going to explain all the scenarios. So please stay tuned. So I hope you enjoy this video. Thanks for watching. Please subscribe for more videos. Thanks and have a wonderful day. Thank you.